If you're building a voice agent for specialist fields, think clinicians, lawyers, engineers, health insurance, medical practice, whatever, the industry-specific jargon needs to be taken really seriously. Okay, we're just going to do it. We're just going to run through it. So I've got here a small clip of very legal terms, right? It's just legal audio, and we're going to simulate what a legal dictation would look like using Cartesia Ink-2 speech-to-text model.
Pursuant to the force majeure provision in Clause 12.3, our client asserts that performance was excused during the relevant period. Jurisdiction remains contested, as opposing counsel filed in Delaware. We will assert privilege over the internal audit documents. Note that the indemnity cap of $2 million per event applies mutatis mutandis to the amended terms. Prepare the amicus curiae brief by Friday.
Okay, great, you go. Now I'm running the script to hit the Cartesia API with WebSocket and actually convert the audio, the legal.wav file into transcribed text. You'll see there are 210 100 millisecond chunks that the code splits it into, and that's because there's about 21 seconds of audio. By splitting into chunks, I'll explain this in a bit, we're basically making sure that it's mimicking a real-life telephony service. And there you go, there's the actual transcription. Now it's actually written to a file here, so let's take a look. Force majeure correct, clause 12.3, I mean, you'd expect that sort of stuff. There's the indemnity cap, we're talking about, there we go, mutatis mutandis, prepared by amicus curiae. So legal Latin also, out of the box, being translated, or rather transcribed, by Ink-2. Now, these are the kind of phrases that most generic speech-to-text models or automatic speech recognition models, ASR models, will choke on, and Ink-2 did not. And this is out of the box, right? This is without key term prompting, which I will talk about later. I've actually got another video on that. But really, this is just Ink-2 out of the box doing domain-specific transcription without missing a beat. So if you're building a voice agent for specialist fields, think clinicians, lawyers, engineers, health insurance, medical practice, whatever, the industry-specific jargon needs to be taken really seriously. If the speech-to-text, the ASR model, transcribes wrong, or its transcripts are wrong, it's going to confuse the downstream LLM, and then that's going to cascade disastrously through your whole voice pipeline. So the agent will do good reasoning on bad transcription, and that's going to lead to bad outcomes in your voice agent. So today, I'm going to be transcribing exactly this kind of domain-specific audio using Cartesia's Ink-2 speech-to-text model and some Python, the kind of code that you drop into your voice agent's code base. We're going to cover 4 domains: field ops, healthcare, legal, and support, and you'll see it all in the code base that I'll share with you. And we'll see how Cartesia's Ink-2, which is now state-of-the-art, handles terms that trip up other speech-to-text and ASR models. We're going to take a quick look at this code right over here, and you will see a design pattern that you really ought to know when you're working with this kind of audio, especially if it's in a conversational voice agent. Now, this code does not send the whole audio file to Cartesia's API in one shot. Instead, it takes an audio file and then slices it into many 100 millisecond pieces and streams each slice one at a time over a WebSocket to Cartesia. Why do we do this? Well, think of it this way. Imagine 2 people are talking to each other. Yeah, it would be weird if one person records everything they're going to say, then sends it to the other person, and then they play it back, because effectively that means the other person has started listening only well after the other person's finished speaking. It would take so long to have a conversation between these two, right? Instead, what the listener is doing in normal conversations, the listener is listening while the other person is speaking, right? So everything that they're saying is streaming into the ears of the listener, and that's what sending slices of audio to the STT model does. It lets the model start listening much earlier. This way, by the time the speaker finishes most of what they're going to say, the transcript is already done, and your listener is not starting from 0 while transcribing. So the ASR, or the speech-text model, is not starting from 0 after the speaker has finished speaking, which means getting the model to listen earlier reduces latency a lot. That's why you want to start slicing it and streaming it as soon as you can when the speaker starts speaking. Now, this actually mimics how in real life telephony audio that people are saying over telephones, gets streamed over to speech-to-text models. So let's start with the first bit of code right here in load wave chunks. What this really does is this function has one job. It takes the wave file, right? The wave file that we're going to be passing in which will be one of these ones here. It takes the wave file and then it chunks it down. It basically slices it into a list of small 100 millisecond long audio pieces, right? And there's some math here that shows you how to convert audio into these little pieces. Now, keep in mind that this is going to be sent over a WebSocket connection. And Ink-2's WebSocket API expects mono, so not stereo, 16-bit audio samples, right? So the 2 bytes is the size of each sample, and uncompressed PCM. PCM is pulse code modulation audio, right? So it's not compressed at all. And so the first bit of logic is doing that. It's taking the WAV file, and it's running get n channels, making sure that it's only one mono. It's getting the sample width, which is the size, which is making sure that it's 2 bytes or 16 bits wide. And then it's getting the compression type and want to make sure that it's actually uncompressed, right? So if it's not any of these three things, we're going to throw an error. The next part is doing the actual slicing of that audio. And here's where the frame rate ends up coming into the picture. Now, you've seen frame rate a lot of times before. Think of any MP3 or a Spotify track that might say it's 44.1 kilohertz or whatever, right? That number, the kilohertz, is the frame rate. It's also known as a sample rate. And it's how many tiny audio snapshots get captured, which is sampled, every second. So 16 kilohertz means 16,000 snapshots in a second. That's the same number that the WAV file's frame rate here gives us. So what you'll see here in the code is that the code takes that number, let's say 16,000 in this case, right? And then it asks a simple question. How many of these snapshots will fit into 100 milliseconds? Now, 16,000 is per second, frames per second. So, and if you're looking at 100 milliseconds, we're saying, well, it's 1/10 of a second. So it's really 1/10 of the 16,000 will fit into 100 milliseconds. Not so, we'll get 1,600 frames will fit into a 100 millisecond slice, right? And that's what we get here with the frame rate. And then and the chunk length is then divided by 1,000. So that's the math here, right, in this piece of code. Now that we know how many frames you're going to include in a given 100 millisecond chunk, which is this frames per chunk variable, we're going to read the frames from the WAV file at that many frames per 100 milliseconds and append that to a list called chunks, right? So we're going to do chunks.append here. And then we return the frame rate and we return the array, the list of chunks. Next, we want to turn to this transcribe with Ink-2 function. This is where the chunks actually get sent to Cartesia, and Ink-2 returns transcriptions really fast. Now remember, for conversational voice AI, the metric that we really care about is the time to final transcript, the TTFT, which is how long it takes to get a final transcript from the model calculated from the moment the user finishes speaking. Okay, this is what determines whether your agent is actually responsive for a conversational AI use case or whether it's always buffering to catch up. So how this transcribe with Ink-2 function is going to work is that the code here opens a WebSocket connection to Ink-2, and it gives in the encoding and the model and the sample rate. Now the encoding here, this PCM16, is really saying it's, pulse code modulation as we talked about before, and that 16 maps to the 16-bit or the 2-byte frame width that we talked about before. Once the WebSocket is open, basically it loops over the chunks, right? The chunks of 100 millisecond audio slices, and then sends it over the socket and waits about 100 milliseconds before sending the next one. Now that wait is important because it's what makes it sound like a live call. We're kind of simulating what a live call would sound like rather than just a file dump on the model. Once it sends all of that, it sends a finalize command saying, okay, we're done with audio input, so now you can just flush out the rest of the transcripts, and then it sends a close command. And after that, we start getting the events back from the Ink-2 model, and it looks for a transcript event and that the event is marked final. It's a final transcript, it's done. And we take a transcript variable that starts off as an empty string, and we just consistently keep appending the text property that comes on the event, right? And then we strip all the white spaces and things like that off it. And by the end of the loop, you've got the full transcript, which is going to be the exact input that your agent's LLM would pick up next, because that's downstream of the ASR. So that's the whole flow, right? You load the WAV file, you check the format, you slice it into lots of 100 millisecond long chunks, then you stream those chunks over to Ink-2 WebSocket, and then once you've sent all the chunks across, you send a finalize command and you send a close command, and then you start collecting the events back from the Ink-2 endpoint, and you assemble your transcript by concatenating the transcript. Now, all of this code is on GitHub, so I'll put a link in the description so you have access to that. I'd encourage you just to run it yourself and get used to this pattern. Run any of the 4 sample files that you see here, the sample WAV files, and you'll see that Ink-2 gets domain jargon right without any extra setup. It just gets it out of the box here, right? You don't really need much of prompting or fine-tuning or any glossary or anything like that. But if you've got specific brand name or unusual spellings that you need to have transcribed exactly because it's important to your use case, well, you can then use key term prompting for exactly that kind of thing. Now, you can look about it here in the docs, and you can see I've done a video here on it as well. Or you can just simply go to the playground and try it out here. You can paste your key terms here and give it a crack. Like I said, I've done a video on that, which you can find in our YouTube channel. So like I said, I will put this GitHub repo up so that you can access it. And don't forget, you need an API key to run some of this code. So you'll get that from play.cartesia.ai. It's free to start, and you can start using the models right away without having to pay anything. So if you have any questions, Reach out to us anytime. We love hearing from you guys. In about 5 seconds, you're going to see a screen that'll show you how you can reach out and find us. And of course, please like and subscribe so you can get notified when we ship new things. And believe me, we're always cooking new things up at Cartesia, right? We're always cooking. Things move really fast around here, which is what makes it so exciting. Okay, we're done. See you next time, guys. Cheers.